The project is about designing a pavilion which corresponds to the movement of sun, which can also be called dynamic architecture.
Dynamic architecture. You say that you've added a fourth dimension, time, to the 3D elements of architecture. You've created a building that moves. How did you get this idea?
As an architect, I design things that could change over time. Not just the shape, but mainly the functionality. Everything is changing. Everything is changeable.
The inspiration for the pavilion was taken from the touch-me-not plan, which is also known as mimosa pudica, which basically closes itself when someone touches it from outside. The location for the pavilion was chosen to be Seattle, a city in Washington, where there is a high percentage of cloud cover and overcast conditions. Data taken from Climate Consultant shows that during the winters, the cloud covers in the area of Seattle is as high as 70%, whereas in summer it drops down to 50%. However, one must not forget the overall percentage remains above 50, which is significant.
With regard to the steel structure, the mild steel structure is made with 12 meter length and 6 meter wide. The height of the structure is 5 meters. The structural analysis is done using the StatPro software. The major loads acting on the frame is the wind load and the dead load. The surface finish for the steel is with 2-layer coating with galvanized followed by the powder coated finish. The roof of the structure is the most elegant feature of our design. The frame of the skylight would be extruded aluminum curtain wall system. Aluminum frame would be the secondary structure transferring the loads from the glass. The finish of the aluminum will be high quality PVDF 3-coat system. The glazing is 6 mm planeable clear light with 16 mm airspace with laminated glass as the bottom layer. The 3 sides of the pavilion is set with the oval-shaped movable lower system. Once the lower blade is in the vertical position, the complete sunlight is blocked, and when it is in the horizontal position, the inflow of the sunlight and the air is maximum. The special sensors are set on the pavilion, which gives input to the processors based on the impact of the sunlight at the time. The pre-programmed processors works based on the input received by the sensors, and the output is given to the motor to move the lever in required angle.
The top area of the skylight is a shading device which consists of opaque acrylic sheets. When the sunlight hits the skydeck, the shading device completely opens into 180 degrees to protect the pavilion from the sun. When the sun sets, the opaque acrylic sheets close itself, which is a similar concept to the touch-me-not, and in subsequent is a dynamic architecture. Furthermore, on the roof there is a sensor which sends out signal to the pre-programmed processor, which in return provides output to the motor, which helps in the angle of movement. Now comparing the pavilion with LEED. LEED, under the section of Materials and Resources, encourages construction waste management solutions such as source reduction, material reuse, and recycling, as most of our material used is either aluminum or steel. This is mostly recyclable, hence the pavilion can score points under this category. The image shown is one of the drawings of our earlier stages. Earlier, our area closer to the ground was exposed to sun, which could have led to significant solar calculations. Hence, the idea was to cover the entire area and only exposing the northern side of the pavilion. The drawing shown is taken during the second phase of the design development. The team thought of replacing the shading devices with the glass roof itself, but later on, the team decided of installing louvers on the east, west, and south side, with also installing the shading device on top of the glass roof that would involve the mimosa pudica concept. For the base case analysis, during the month of April, the suncast results showed that the sun rises at approximately 5:15 in Seattle, with shadows on the western side, and as the sun reaches its zenith and fades away, the shadows shift towards the north eastern side with sunset at about 7 o'clock in the evening. For the summer season, Seattle faces up to 16 hours of daylight, with sunrise taking place at approximately 4:30, with shadows towards the west side, and as the sun fades away on the western side, the shadows appear on the north and east side. Whereas in the winter season, Seattle faces of about 8 hours of daylight, with sunrise taking place at about 8:30 in the morning and with shadows in the northern side, and sunsets at about 4:30 in the afternoon. To determine the lux levels, dialux software was used. The image seen is the plan view of the pavilion along with the lights indicated. The lights were installed on the slip roof on each side as well as on the flat roof, and the arrangements were given by the dialux software, and on the east, west and southern side the louvers were placed. The arrow points are towards the north. Moving on to elevations, it can be seen that the louvers are installed on the southern side as well as on the east side and as well as on the western side. As far as the design is concerned, the northern side should have been open, but for the dialux calculations we have shown it as a wall. And for the lights, it can be seen that the lights are installed at the roof. Moving on to results. The lux levels for summer season were found to be around 435. As per leadership in energy and environmental design, the lux levels should be greater than 300. In our case for the pavilion, during the summer season, the criteria was met, hence the results are satisfactory. However, during the winter season, the lux levels were not that great. As per lead, the lux levels should be greater than 300. However, in the winter season, the lux levels were as below as 30, which is not that satisfying. The reason for low lux level can be due to two reasons. Number one, the less amount of daylight in Seattle during the winter season, that is approximately 8 hours, and overcast conditions. For renewable energy resources, wind power was considered to be the most optimum option because as per US Energy Information Administration, the state of Washington has one of the highest wind power capacities. Referring to the data extracted from Climate Consultant, it can be seen that Seattle's average wind speed is approximately 4 meters per second, which is ideal for wind power generation. To determine the electricity required for the pavilion, wind power calculations will be necessary. The air density is 1.23, whereas the radius of the wind blade is kept as 5 meters, and whereas the wind speed of Seattle is 4 meters per second and bed's limit is taken as 0.4. Based on the values shown, the power was estimated to be around 1236 watts. One must note that this much power is not enough to meet the demands of the pavilion, hence additional wind turbines may be needed. Furthermore, power generated by 14 LED lights installed in the pavilion had an energy consumption of 1681 kilowatt-hour per year.